Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very happy to have Sal Torquato speaking this week. He's affiliated with many different departments at Princeton University, and he'll be speaking on particle packing problems for fun and profit. And I have to say, this is one of the few times a later colloquium speaker has ever complained about the title of an earlier talk. This person wanted to use for fun and profit in his own talk, and now feels that he'll look like he's copying Sal. So thanks for speaking.
Thank you very much, Henry. It's a real pleasure to be here. Is this too loud? It is? How do I bottom? Am I speaking too loud? It's fine?
I think Jeff heard and adjusted it.
Oh, okay, great. All right, so the first thing I want to do is mention, because people are always intrigued by my affiliations, is to say that the intersection of my departmental affiliations with the subject areas of my degrees is the null set. And it's up to you to figure out at the end of the talk what my degrees are in. If you want to go to look at some of the papers that I'll be talking about today, you can go to my website, which is very easy to remember, cherrypit.princeton.edu. Okay, so Henry asked me to try to motivate the talk, because this is going to be for a general audience, and I want to start out by saying that these are very, very simple problems to state, packing problems, notoriously difficult to solve, and they're also very ancient. So Bernal says, in closing, we must not forget the commentary on random packing with which St. Luke attributes to Jesus. Given, it will be given unto you. Good measure, pressed down and shaken together and running over. For by your standard of measure, it will be measured to you in return. In other words, when you went to the market to get your grain, got your basket, and you shook it up until you got the highest density. This idea is actually due to Bernal. It's called random close packing, okay? And it's thought to be the highest density that a random packing can attain. The problem with this is, of course, that no one ever defined what randomness was. And if you think about close packing, it's the opposite. You think of something that's maximally coordinated, like a lattice, which is the opposite of random. Of course, Kepler studied the best way to stack cannonballs on the decks of ships. His solution to the problem is called Kepler's conjecture, which I'm sure a lot of you know about. Okay, so I'm considering to begin with hard sphere packings, which means simply that I'm going to have identical spheres, and they don't feel any force when they're further than a diameter apart, and they feel an infinite repulsion when they try to overlap. Now, it turns out this model is used in physics for to understand the structure of dense many-particle systems with short-range interactions. For example, liquids, glasses, crystals. It's used to understand colloids, granular media. Now, why is it that, for example, a typical interaction that you would have in a simple liquid like argon, this is a Leonard-Jones potential, so you have a very steep repulsion and then short-range attraction. Why is it that you could basically replace that in terms of understanding the basic features of the structure with just this hard sphere potential? It's basically because the repulsive forces are primarily responsible for determining what's going on at high densities. Okay? And I just want to remind you what a classical ground state is. A classical ground state are those classical particle configurations with minimal potential energy per particle. Okay? And just to drive that point home, I want to show you a simple animation of a molecular dynamics of atoms interacting with this Lennard-Jones potential. It started out as a liquid, okay? And you imagine that I've slowly cooled this liquid. It undergoes a first-order phase transition to a crystal, okay? This is before it's taken to absolute zero. It's on its way to absolute zero temperature. And you can see that this is a very ordered arrangement. And in fact, it turns out to be, if you go to absolute zero, it turns out to be one of the close packed structures for the sphere. Sorry. These are periodic boundary conditions. So every now and then, you're going to have particles moving in and out of the box. Okay. Now, suddenly this got, unless my voice got louder all of a sudden. So the point is that this is if you go to absolute zero, this is a classical ground state. And the hard sphere, the densest packing, is intimately related to this classical ground state. So if you know something about hard particle packings, you actually know something about these kinds of ground states. That's the basic punchline. Okay, and I also said, now some of you may not know what a glass is. Well, what I just indicated to you was I started out with a liquid, I slowly cool, and then this is volume versus temperature, sorry. And you undergo this discontinuous change from this large volume to this smaller volume. And then if you continue cooling, you go to this ground state. On the other hand, if I don't slowly cool, I do it very rapidly. I can actually go to a very mysterious state of matter called a glass, not necessarily your window glass. What I mean by this is that if you look at the atoms, they look structurally like a liquid, disordered. But unlike a liquid, it doesn't flow. It has the rigidity of a solid, right? Rigidity of a solid. And it turns out that random packings of hard spheres have actually something to do with that. You can make a glass out of essentially almost any material if you cool it fast enough. You can make a glass out of a metal. Normally you think of a metal as being a crystal. That's right. I'm going to be more precise about that in a second. As measured, for example, by the pair correlation function. Now, one question I'm going to ask throughout this talk is, can ground states ever be disordered? Can you actually cool something, and instead of going into a crystal structure, it goes into a disordered state? Now, mind you, this glass is metastable with respect to the crystal. If you allowed it to relax long enough, it would eventually go back to the stable state. What this means is I'm reversed. It's not a glass. It's actually a disordered ground state. And any crystal is metastable with respect to that state. Okay, so it's very, very unusual. Packing problems arise. They're ubiquitous in biology. These are just a couple of examples. These are proteins, actually. Okay? And you can see that it's a packing problem. This is a viral capsid, the coating of a virus. Lots of times it has icosahedral symmetry. This is an empty vessel. And the basic type packing problem here is you have to pack DNA inside the virus. So what's the best way of packing it? Now, of course, there are other considerations such as bending energy and stuff like that. But basically, it's a packing problem that involves polymers, long chain molecules. Okay, now let me, if I can, just go to some definitions. So a collection of non-overlapping congruent particles in d-dimensional Euclidean space. I'm going to be working primarily in the Euclidean space. Is called a packing. The density, phi, of a packing is the fraction of space covered by the particles. Okay, a lattice packing I'm going to just show you pictorially what I mean by a lattice packing. What you imagine is that you have particles, and in certain directions you translate them, okay, periodically like this. And it turns out whenever you have a lattice packing, there is this so-called fundamental cell, which is this rhombus right here. And the fundamental cell contains exactly one particle in it. This is a lattice packing of non-spherical particles. And the main point I want to illustrate there is that if they're non-spherical, they all orient in the same exact direction. Okay. So if the volume of the fundamental cell is this, then the fraction of space covered is simply the volume of that particle divided by the volume of the fundamental cell. Then a more general notion, I have this habit of going to my laptop. A more general notion is a periodic packing. A periodic packing is one in which, what happened here? Okay. A periodic packing is one in which you still have a fundamental cell with particles on the lattice sites, except now I can place additional particles within the fundamental cell, in general anywhere that I want, subject to the non-overlap condition. And then these are repeated, see? Now, in the case of a non-spherical particle situation, they can have different orientations. And so the density here is just simply the total number times the volume divided by the volume of the fundamental cell.
It's like one equivalent number.
That's right.
That's needed.
That's right. Mm-hmm. Yeah, you could. Mm-hmm. Now here's another thing, just another couple of definitions that I'm going to use that I'm going to ask you to remember for later. A particle is centrally symmetric if it has a center C that bisects every chord through C connecting any two boundary points. So for example, this square-like particle, this is the center, and I'm drawing chords that intersect the perimeter, right, the boundary. And you can see that it bisects those chords that pass through it. So this is centrally symmetric, and it has two equivalent perpendicular axes. They're both this length and this length are the same. An ellipse is centrally symmetric, but generally it has two inequivalent perpendicular axes. And then finally, a triangle is not centrally symmetric, and neither is its three-dimensional analog, the tetrahedron, which I'll talk about later. All right, so the outline of the rest of the talk, I'm going to say something about sphere packings in low dimensions. The low-dimensional problem, there's actually still a lot that we don't know. Then I'll move to high dimensions and ask, does disorder actually ever win? Finally, I'll go to non-spherical particle packings, and I'll focus, for the most part, on the Platonic and Archimedean solids, which is a recent work. All right. So the sphere packing problem is extremely simple. What is the densest arrangement of identical spheres in d-dimensional space? And in 2 dimensions, we know the best way to stack pennies is the triangular lattice. Okay, that has a density of about 91%. This was proved earlier than Feschtolf, but this is the best proof that I think exists, why this is the best, the densest. Kepler, as I said, conjectured the way your grocer knows how to stack oranges, right, is the densest way, and all of its stacking variants. And that was only recently proved by Hales, and in some sense you wonder if it's even the way that one thinks about a mathematical proof, because it took 5 years for people to check the paper, because it involved computer algebra, And I don't think anybody actually went through it enough to be able to say, yes, everything is correct. And so the analytical part of the proof was published in Annals in Mathematics, and the computational part in Discrete and Computational Geometry. Now, in certain sufficiently low dimensions, optimal packings are believed to be lattice packings. And there are certain dimensions that are amazingly symmetric and dense. For example, in dimension 8, the E8 lattice, in dimension 24, the Leach lattice. Already in dimension 10, the best known arrangement is a non-lattice, in the sense that I described it earlier. In other words, it has more than one particle in the fundamental cell. Now, as soon as you allow the possibility for more than one particle in the fundamental cell, then you're allowing for the possibility that in the limit, you actually can have an infinite number of particles in that fundamental cell. And then if the situation is adjusted properly, you could actually make it a disordered packing. Okay. Now, let me just say a few words. This, I think, is a really interesting question. So for those of you who are computer scientists, I would love to hear your thoughts on this. This is a little different than asking what is a good pseudo-random number generator. It's sort of in that vein, but of course, this has to involve spatial information. So the idea is, if I have a configuration, this is actually the nearby galaxy distribution. And actually underneath the image, if you go to that webpage, you'll see something like, is the universe random? Okay, that was the question. So one way of possibly doing this is to devise scalar order metrics. Now, these scalar order metrics could actually be inner products of vectors, but let me not get into the details. Say I have order metric psi that goes between 1 when you're completely ordered, say, for example, for this, the FCC, and 0 when it's completely disordered, say when it's a Poisson distribution, spatially uncorrelated points, and then everything in between. So the idea would be to devise something that's consistent with our intuition. You rank perfect crystals highest, perturbed crystals, quasi-crystals, highly defective crystals, correlated random systems, glasses, such as what I call the maximally random jam state, and then finally at the bottom, uncorrelated random systems, the Poisson distribution. Now, I'm not going to have time to get into how you do this. Well, let's imagine you can do it. Now I have to introduce some other definitions. And this is just a partial way of characterizing sort of the mechanical stability of the packing. And it turns out to be a really important way of classifying packings. First, you start out with the least stringent, locally jammed. So if I could, let me just draw it here. In 2 dimensions, this particle cannot translate. It's trapped. Okay? If I have d plus 1, not all in the same hemisphere, then this is locally trapped. If all of the particles in the packing have that property, then the entire packing is locally jammed. However, I can have, say I have, this is part of the packing, and now I'm going to extend it. I have a hexagon, and I keep on extending it. All of these have 3 contacts, so they're all locally jammed. But there's a hexagon here that allows me to rotate it, and then the whole thing falls apart. This is not collectively jammed. So you have to disallow any kind of collective motions for it to be collectively jammed. And on top of that, the most stringent one is strict jamming. This means now I have to, I cannot, at the boundary of the sample, whether it's a periodic boundary condition or a container, I can't shear it, I can't compress it. So that's the most stringent form. And it turns out that you can test for all of these categories. So if you hand a configuration, to me or to Henry, you can test it rigorously using linear programming techniques. All right. Now I'm going to show you a way of thinking, bringing those two previous ideas, jamming as well as an order metric, into what I call an order map. So imagine, psi is simply a function of the configuration of the packing. So you give me a configuration and I will spit out a psi value. So any packing configuration then will be a point in this plane. The order metric. One being the most ordered, this is the most disordered. Now, it turns out, it may be against intuition, that you can actually achieve locally jammed packing that go to 0. You can still achieve this local packing condition. So for local packing, the set of local jam structures extends from 0 to 74%. I'm showing this in 3 dimensions, 74% being the Kepler conjecture structures. Now, if you think about collective jamming, it has to be a smaller set. And then if it's a finite system, then these two are not equivalent to each other. They become equivalent in the infinite system limit because then the boundary is not important. But the point is that any point, this is a convex hull around all of the jam sets. And the point is that the locus, that boundary, are all extremal points. And some of them are really quite interesting. So, well, B, of course, is the FCC, the Kepler point. It has both the highest order and the highest density. B prime would actually be one of the stacking variants of the FCC because there are infinite number of ways of stacking. And this presumably would be the one that has the most disorder. This point has the lowest order metric. So that's the maximally random jam state. This is the one that corresponds to what I was showing you earlier as a glass. Okay? So remember, it's a prototypical glass in the sense that it's maximally random, subject to the condition that it's jammed, and in fact, the shear moduli are infinite, and so is the bulk modulus. So it really is a prototypical glass.
Could you explain a little more about the zero volume locally jammed package?
Oh, yeah, sure. Absolutely. But do you mind, let me just finish this one point, and then I'll return to that, because that's also very counterintuitive. This is an interesting set of points. These are the lowest density jam structures. Okay? And usually the physicists don't. Are there any physicists in the audience? No, I'm kidding. Usually the physicists don't really bother to look at those points. Why? Because they use Monte Carlo simulations with random initial conditions, and then they would never see these kinds of structures that I'm going to show you.
How do you figure out these plots?
Very good question. So most of it is schematic. The density locations are what we know currently for those extremal points that I've identified. Okay? Yeah, I'm going to get into that. Yep. Okay, let me answer your question. Well, they turn out to be very, very wispy structures. Okay? So imagine, if you will, 3 layers, okay? 3 layers of particles. But now I'm going to have a very, very slight curvature to those layers. And then you basically are making filaments out of them. And there's a way of filling the periodic cell in such a way that in the limit, basically that's the idea.
The one you drew for us in the center.
Oh, absolutely. This is poor. That's a poor. That's a great question. Those are inaccessible. So in other words, you're never going to be able to find at 74%, okay, an order metric that corresponds to the ideal gas.
Okay, so I still don't understand how you figure these things out. And then how you make these plots.
Well, B, that is easy, right? B is easy. Because that's the Kepler point, right? B prime is just according to your order metric, you're measuring one of the random stackings as the most disordered, so that's easy. This.
So you're only saying making kind of qualitative relative comparisons between these 5 points. You just know
That's right, but we also have some experience which I haven't told you about in actually measuring them. So I don't want to get into it because this is not the main part of my talk. And then these I'm going to show you now. So this actually is, this is what I would call A here. Okay? Now what is this? This is the FCC. It's an amazing structure. You can go along a diagonal and remove an entire row of spheres without making it fall apart. And the square root of 3 away, if one is the diameter, you can have another tunnel, infinitely long, and so on and so forth. And you have parallel tunnels that run through the entire FCC structure. You actually are removing 1/3 of the particles. So this has 2/3 the density of the FCC, about 49%. And
wiggle the boundaries of that, it won't collapse?
what's that?
If I wiggle the boundaries of that, it won't collapse?
No. And in addition, good question, and in addition, each particle contacts 7. If I remove one single particle, the whole thing will fall apart. It's right at the cusp of stability. Okay. You would never find this in a Monte Carlo simulation. Never. Okay. That's right, when you try to deform it. This is from all of our experience with simulations, because this is the only way you could attack it, MRJ. Now, it's not telling you much, but I'm just showing you what a typical configuration would look like. On average, you have 6 contacts. This is the FCC, and of course, there you have 12. Okay. But it's really a different way of looking at packings. Now, let me say something about the pair correlation function. Basically, you pick a particle center, okay, imagine, and you look at all of the pair distances between this and all of the other particles in the system. And you do this for every single particle in the system. And you just build a histogram. And you normalize it in a way that for a random system, and in particular for the maximally random jam state, which is supposed to have this magic number, mysterious universal number of 64%, which I don't buy for a second in terms of it being, mysterious and universal. It happens to occur at 64%, but the point is you never can get away with characterizing a complicated object as a packing with simply the density. Okay, I consider that nonsense, but this happens all the time. Okay, so here you have on average 6 contacts. So there's actually a delta function at contact. But the main point that I want to illustrate is that this will decay to unity. Okay, so that's the way it's normalized. Now, if you do the same thing for FCC, right, what are you going to get? You're going to get direct delta functions at all of the lattice vectors. If you do a radial average, it's just going to count all of them at a particular radial distance. So the heights are simply determined by how many particles you'll find in that shell. Okay? But here's the really important thing. In low dimensions, notice you have a gap between 1 and the square root of 2. And between the square root of 2 and the square root of 3, and so on. That gap helps you in low dimensions to give you the highest density. Those gaps in high dimensions will kill you. So keep that in mind. Okay, so why the interest in high dimensions? Well, people in physics are really interested in these questions now. Of course, in discrete geometry, number theory, string theory, and I guess a lot of people here know in communications theory, Shannon showed the best way to send signals, amplitudes at d different frequencies. So this is now a d-dimensional coordinate. Over a noisy channel corresponds to the densest arrangement of spheres in that d-dimensional space. And here's just a simple cartoon to illustrate the point. A channel will have a maximum error associated with it. So if we come up with a code book, all right, and these are the code words, say 1, 2, 3, nearby code words. And if you, because of the channel characteristic, you say, okay, the error when I send it, the largest it can be is within this sphere, right? And I put such a sphere around every single code word. If the point goes there, what are you going to say? It was 1, 2, or 3. So the point is, what you want to do is you want to have a code word, a code book, so that they're at least a diameter apart. That's a packing. Why is it the densest packing? Because you want to fit as many words as possible per unit volume. Each dimension has its own distinct properties. Turns out lessons that you learn in low dimensions almost invariably never help you in higher dimensions.
Why do glasses and liquids give you packing problems?
Why do glasses and liquids do? They don't. People look at it in high dimensions to gain insights into low dimensions. So people in physics do that all the time. So in the Ising model, you don't necessarily restrict yourself to low dimensions. You go to high dimensions, the problem simplifies somewhat, and yet you can gain insight into what's happening in low dimensions. Okay, so the point I want to make, yes, sure, yes. Yeah. Well, at least the ones that we know, the best packings. That's right. That's definitely correct. That's definitely correct. Yeah. Okay. So the point I want to make here is that lattice packings have a lot of empty space. Okay. And if you take just the simple hypercubic lattice, right, and you imagine that the spheres have radius 1, and you look along the diagonal here from the vertex perpendicular to this, the tangent to the circle, that distance is the square root of d minus 1. So already in dimension 4, you could add another sphere to the problem and double the density. That means that in sufficiently high dimensions, all lattice packings are almost surely unsaturated, meaning I could always add another sphere to the packing. In other words, these are generally not going to be good packers in high dimensions. I'm going to skip this. For large D, the best that one can do, first of all, there's no proof beyond dimension 3 of what the densest packings are. The best that one can do is devise upper and lower bounds, because it becomes extremely difficult, in fact, to even construct good lattice packings. Yes?
So why are you interested in higher dimensions?
Why am I interested in them? I could say the true answer is that I'm not a chemist. Okay, that's actually, I would say, go back to the title. Literally, I'm not being facetious. I find it fun. Literally. I mean, I looked at it because it was an interesting thing to do. And I didn't even know when I entered the field that it had anything to do with communications theory. I just thought it was, literally, I thought it was fun. Does that satisfy you? What? You're a communicator? Okay, so I didn't even know when I started this. I did something where we were doing it. I'm going to explain it later, actually. So to answer your question, I'll come to a point in my lecture that makes the direct connection to Henry to try to answer that question.
It's also interesting because in physics you go to higher and higher dimensions because you end up
Right.
system in high dimensions, but yours is so different.
It's really different than mean field because in mean, you already have, with the Ising model, the critical dimension is 6. And here, you don't have such a thing. Okay, so let me just say something about Minkowski. Okay, so he was thinking about lattice packings. You guys are smiling a lot. Okay. So he was interested in lattice packings. And of course, because of the reason you mentioned, right, we know that the highest density has to go to 0. So to be able to just show that there's a lower bound on the maximal density is an important mathematical thing to do. So it's in terms of the Riemann zeta function, but effectively, let's set that equal to 1 because that becomes 1 very quickly. And so everything really is controlled by 1 over 2 to the d. That's the controlling exponent. It's non-constructive. He doesn't tell you it's this lattice. He just says basically they exist. No one has been able to provide any exponential improvement on the dominant asymptotic behavior. For large d, the best lower and upper bounds respectively are of this form. And like this is, you can't make this up. This is a wonderful name to have if you work in sphere packings. And the only improvement that you get is linear in D. This is for lattice, again. This is not. This is for any packing, Kabatinsky and Levenstein. And of course, that tells you that it has to go to 0. These should be max. But the point is, to get exponential improvement, I want this coefficient 1 to be something smaller than 1 and greater than that. Actually, there's a student of Henry's who's recently done some stuff that improves the constant in front of Boltzmann. No, not asymptotically. Henry has a better result in lower dimensions that I'm going to talk about. Okay, just to give you an idea of some of the strange things that goes on. Take the density, multiply it by 2 to the d, which means Minkowski's bound has to saturate, right? And take the hypercubic lattice, okay? The hypercubic lattice actually goes way below this Minkowski bound very quickly in dimension. It just means it's a poor packer. But so does one of the generalizations of the best packing in 3 dimensions, which is also thought to be the best packing in 4 and 5 dimensions, the checkerboard lattice. Okay? Look at where the Leach lattice is. I can't show it on this scale. All right, so now I'm going to tell you this approach that we took. This was published in Experimental Mathematics, which sounds like an oxymoron, but it's a real journal. So it's based upon a conjecture, so we can only call it a putative improvement on Minkowski. If this was true, then it would mean you can find continuous potentials like Lennard-Jones in these high dimensions. By the way, this is saying, I should say, I didn't tell you the punchline, that it suggests, the way we do this is it suggests that the densest packings are in fact disordered. In other words, a pair correlation function that decays to unity for large R. If that's true, then it would imply that for some continuous potentials, you will have ground states that are completely disordered. Okay, so existence theorem for point processes. So a necessary condition for the existence of a non-negative pair correlation function, the one I talked about earlier, of course, since that's a probability, it has to be a positive quantity, is that basically its Fourier transform, the analog of its Fourier transform, S of k, has to be non-negative for all k. Okay, that's the basic statement. Now, these are not sufficient conditions, they're necessary conditions. So just because you can concoct, and that's what I'm going to be doing, I'm going to concoct test functions, test pair correlation functions, that satisfy this condition, and I'm going to pose it as an optimization problem. The parameters in my hypothesized function are denoted by A. That's what I'm going to optimize over. I want to maximize the density over that set of parameters, such that this condition is obeyed. That's it. That's the optimization problem. Excuse me? You've got me. It is. Okay. Now, the highest density that you can get, I'm going to call phi star. I'm going to call that the terminal density. If a packing exists, then immediately I have a lower bound on the highest density. Okay? Is that okay? No, that's the issue. Because I'm going to explain that. Now, this brings me to one of the reasons why I believe that mathematics is not invented, it's discovered. Because unbeknownst to me, Henry Cohen and Noam Elkies were devising the dual infinite linear program to the problem that I just described in the previous transparency. We were coming at it from, like I said, it was in this modest journal, a physical journal, and just as a lark, I said, let me just see what happens when I do this in any dimension, and I found out that the result improved on Minkowski's bound linearly at that time. And, because I just read on Google what Minkowski had done. That was my first introduction. And then I became a little more serious about it because there were mathematicians at Princeton that said, if you can actually get the exponential improvement, that would even be better. So that's how it actually started. So it's almost serendipity. And what's beautiful about what they did is that unlike our program, which involves test pair correlation functions, they have test pair potentials. Okay, that's what it turns out to involve. And the fact that they have an upper bound proves that what we thought was basically, at that time, just a density estimate, proves that it could never exceed the upper bound. And since then, they've proved that there is no duality gap between the upper and the lower bound. In other words, there's an optimal solution. All right. So another thing that they did, which really deserves mention, well, actually, subsequently with Abhinav Kumar, they used the LP bounds to prove that the Leech lattice, first of all, is the unique densest lattice in dimension 24, and that no sphere packing, whether it's a lattice or not, can exceed the density of the Leech lattice by a factor of more than 1 plus 1.65 times 10 to the minus 30th. And in fact, they could actually make this number 30, 50 if they want to. Okay. So between friends, that's really, really close to a proof. And they proved a very similar result for the E8 lattice. Okay? So almost surely those are indeed the best packings. Now, what is really amazing about this is that these are really miraculous dimensions. Why? Because in those dimensions, it means that pair information is enough to get sharp bounds. Okay. For example, if you apply these techniques in 3 dimensions, you don't get sharp bounds. Otherwise, we would be proving Kepler's conjecture. Okay? So that means that in these other dimensions, information beyond that contained in pair information is required. Yes, yes, yes. Now, let me just say, I'm just going to quickly go over this just to show you that, in fact, disordered packings immediately come to the fore and tell you something very interesting, because you can actually construct exactly a disordered packing for which you know all of the correlation functions, G2, G3, G4, G5, and all of them. So you can characterize it completely. And you can show, roughly speaking, that as the dimension goes up, that basically the pair correlation function tends to the step function. And it has a density of 1 over 2 to the d. Now, by the way, that is what? That's Minkowski. So with this is an exact construction. Now we're not even talking about realizability. This exists. And the interesting thing about this is if you compare it to the d-dimensional, the checkerboard lattice, which generalizes the FCC, and you go out from a central particle, you just go out a distance, a square root of 3, and you count all of the spheres inside that sphere, okay, from that central sphere. The ratio in 100 dimensions for this disordered packing to the checkerboard lattice is 10 to the 13th. Okay, that's a stunning number. Well, this is something that we already knew in some sense, right? Because we showed it goes below Minkowski, well below, 100 dimensions. But it's interesting to know that you could actually get a disordered packing that actually does it. Okay, so basically the conjecture is the following. A disordered packing is one in which G2 decays to unity faster than that power. And essentially the conjecture says, look, in high enough dimensions, the two necessary conditions that I mentioned earlier become sufficient for the existence of a packing. Now let me explain why. So one is this there's a decorrelation that takes place, which I'll explain. What I mean by that is unconstrained spatial correlations in disordered sphere packings that may be present in low dimensions vanish asymptotically in high dimensions. I'm going to go quickly now and just show you, these are computer simulations of the maximally random jam state in dimensions 3, 4, 5, and 6. These are the pair correlation functions. Whoops. This black line is 3 dimensions. See, in 3 dimensions you have this spiky structure. In 4 dimensions, this almost disappears. And you go to 6 dimensions, and now you can see the amplitudes of the oscillations really diminish. So in this case, because it's MRJ, there's really a delta function at contact. But what this is saying is that you have a delta function, and then you have something that's tending to a flat step function. You could already see it in low dimensions, which means that, roughly speaking, you can think of all of the higher order information that normally would be required to specify a packing is somehow encoded in G2. Okay, that's what is really being said. All right, so now if I blindly apply the conjecture with just the step function, there's no optimization really involved. And what you get is 1 over 2 to the d, which is Minkowski. So this is, you can think of it as being consistent with Minkowski, but it was derived for a disordered test function. Now what you do is you put a delta function here, z, the strength, that you optimize over. And now, lo and behold, you recover, for this disordered test function, balls bound, that form. The next thing is you allow a gap to exist between the delta function and the step function, and you have a parameter, an additional parameter now that you optimize. And this is the one that actually gives the putative exponential improvement. Just to show you, if we go to Conway and Sloan, This is the best lattice packing in dimension 56, and in dimension 60, it's below this lower bound. This is the actual exponent, and that's the numerical value that you get. This also gives you a maximal kissing number that beats the best known rigorous one. In addition, if you include more delta functions, the exponent does not change. So it suggests that the exponent is really robust. It would be amazing if it was actually the right answer. Okay, now I'm going to move to other particle shapes. Yes?
If you were allowed to pick two diameters
Yes?
and pack, say, in 3 dimensions,
Yes?
what would you pick and how would you pack them?
Oh, I mean, if I wanted to pack it efficiently, I would make one really small compared to the other.
But you can actually compute what they would be and what would be the best.
Yes, except really there's much less known about when you have different sizes. Much less is known. And people have, studied those problems, but not as much as the equal size. But that's what I would do. Okay. So until the last several years, very little was known about dense packings of non-spherical shapes. From a fundamental point of view, you would like to understand what happens when you allow the particle to have rotational degrees of freedom. Ulam conjectured that the maximal density for packing congruent spheres is smaller than that for any other convex body. No, he wasn't alive in 2001. But it's from Martin Gardner's book, I should have mentioned. It's from Martin Gardner's book, who quoted Ulam, who must have had a conversation when he was alive. But right, you're right. Okay, so the practical relevance, of course, life is not a bowl of spheres. This is a buckyball, okay, carbon C60, which is really the truncated icosahedron, which is one of the Archimedean solids. So if you understand packing, for example, of those kinds of solids, you might say something about buckyballs. Okay, this is how it all started. This is my colleague, Paul Chaikin, who used to be in the physics department at Princeton. And one day his student, these are peanuts, so this is not what we worked on. This is too tough. It was the plain M&Ms that we actually worked on. And his student went into the lab, said, M&Ms pack more densely randomly than spheres. 68%, not 64%. He didn't believe him. He redid the experiment, and he found that they were 68%. I'm going to tell you. That's a good question. So we thought, a naive guess would have been, look, an ellipsoid is just a simple deformation of a sphere. It's an affine transformation, right? So, and the volume fraction is invariant. So I said, Paul, I don't trust this because I can't see what's happening inside the jar. Maybe there's some ordering taking place. So I suggested that we take it to the Princeton hospital. And we actually did a full head scan MRI on it in between patients. And in fact, now with this MRI, you could actually see there was no orientational order. It's amazing. Now it turns out that, what was the lesson that we learned here? This is when I became interested, and I had one of my students, Alexander Donoff, to actually do non-trivial molecular dynamics simulations of ellipsoids. So in M&M, you're stuck with the ratio basically 1:2 aspect ratio. And it turned out that was not the optimal shape. And there was a shape that was much closer to the sphere that gave you a random packing with the density of the FCC crystal, 74%. So this is a this is a plot of that versus aspect ratio, which I'm going to skip for the moment. So this raised the possibility, we thought, oh, wow, maybe we found the object that packs randomly more densely than any crystal. Wrong. Because we have a non-lattice where what you do is you place the first, say you place spheres in a hexagonal layer, and then you do an affine transformation in this direction, right? So you have ellipsoids. Now, instead of layering the next layer in exactly the same direction above it, you layer perpendicular. And then you do AB, AB, AB. And once you reach an aspect ratio of the square root of 3, or 1 over the square root of 3, you get the highest packing fraction that we could attain, which is around 77%. Now, why does this happen? Well, clearly it's the rotational degrees of freedom. But we really didn't understand it. Now I'm going to say something about superballs. Superballs, this is just the sorry. Yes? Yeah? No. No. Okay, so that's, no. I'll tell you. That's a common misconception. And the reason why it's a common misconception is what I showed here earlier. If I stretch, this takes up 2/3 the volume of the cylinder. If I stretch it, no matter how much, it still will take up 2/3 the volume of that cylinder. And in the same case here, if I squash it, people say, well, you have a pancake. And you can stack pancakes one right on top of another, and you're going to definitely get a higher density. Well, it's the same problem. It's not really a pancake. The curvature matters. Okay, so with superballs, okay, so the P is what I call the deformation parameter. When P is equal to 1, you have a sphere, a d-dimensional sphere. If you make P go to infinity, you go towards a cube in 3 dimensions. If you make it 1/2, you have an octahedron. This is a slightly smaller value. Then if you keep on going, you have a 3-dimensional cross. So this is a nice way to parameterize going from convex objects all the way down to concave. And very little is known about concave. Okay, the moral of the story here is that, and I'm not going to bother to go through this, but just to tell you, the basic punchline is that superballs, at least when you're talking about the convex regime, the densest packings are apparently lattice packings. So you definitely have rotational degrees of freedom here, right, that you've introduced. You break the rotational symmetry of the sphere. You did the same thing with the ellipsoid. In one case, you get a non-lattice. In the other case, you get a lattice.
Wasn't that a lattice that you showed us for the ellipsoids with the AB layers?
No. Okay. Okay, so yes. A physicist would call a periodic packing a lattice. I'm using the mathematicians. That's right. Exactly. Yeah. So that had a 2-particle basis, which I'm calling let's say non-Bouvet lattice. Okay. Now let's go to Platonic and Archimedean solids. So the difficulty of, when you see now something like a polyhedron, you say to yourself, what's going on with this? I mean, there's rotational degrees of freedom clearly, but now you have flat faces, you have non-smooth faces, right? You have sharp corners. So this actually was recently published, made the cover of Nature, and then we did something this is actually what I call a tabloid, okay? So we reported the results in a tabloid, and then the real stuff is reported here. Okay. So the Platonic solids, convex polyhedron with faces composed of congruent convex regular polygons. There's only 5 of them: tetrahedron, icosahedron, dodecahedron, octahedron, cube. Cube is the only one in the tile space. Among these 5 Platonic solids, this is the only non-centrally symmetric one. Archimedean solids. Semi-regular convex polyhedra composed of 2 or more types of regular convex polygons meeting in identical vertices. There are exactly 13 of them. One I want to bring your attention to is this one, the truncated tetrahedron. What you do is just lop off the corners, right? And you end up having hexagons and triangles. That also does not have central symmetry. The other 12 do. Okay, so you say to yourself, well, how are these things going to pack? Well, let me start. The story here began really with something that I did with John Conway. First of all, regular tetrahedra cannot tile space because you have a dihedral angle that is not a submultiple of 2 pi. Okay, so then the question becomes, how well can you do? If it can't tile space, how well can you do? So the densest lattice packing, and again, Brevet lattice packing, was obtained by Hoylman, is the best one. And look at how poor the density is, around 37%. And the reason is that, remember, in a lattice packing, you have to point the particles, all the particles, in the same direction. This is just not good. You're not really exploiting the rotational degrees of freedom. So John Conway and I wrote a paper where we thought we were really clever. We came up with a 20-particle basis, 20 particles in the fundamental cell, got around 72%. It didn't take long for actually a graduate student in the math department at Michigan to come along. She evidently had obtained physical models of tetrahedra and played with them, and then put it on the computer and found an 18-particle packing that actually demolished what we had. At that point, I said, forget about trying to come up with clever constructions. So it was clear that if you're going to do something with this problem, you have to have a good algorithm. And this is basically a sketch of the algorithm. What you do is you put particles in a box. This is the fundamental cell. Remember, this is going to be periodically replicated. And what you're going to do is you're going to make particle movements. So, for example, this particle wanted to go here, but it overlapped, so you're going to reject that. You're going to rotate the particles. But not only that, you're going to actually do a search among the space of lattices. So the lattice vectors are changing. Okay, so that's part of the optimization. So it's an optimization program in which you're exploring the particle configurational space, the space of lattices, to get at least a local minimum, hopefully a global minimum, in negative of the density. Okay, that's the idea. Now let me show you the result. So in the Nature paper, we used a 72 particle basis, okay, to get 7A2, which is not a tremendous improvement over Beth's Chen's. And you can see that they basically like to consist of these kinds of wagon wheels, where you have 5 basically around a common vertex. Then in this later paper, we have a 314 particle basis. And you can see that that is significantly higher. Now what's really interesting is that you can analyze this structure using the pair correlation function and other statistics. And what you see by eye is actually verified with the correlation functions, that it's in fact more disordered than that one. So here's the picture. You not only increase the complexity of the fundamental cell and get a higher density, but you also increase the disorder of the system and you get a higher density. Very strange, very strange. And so it raises the amazing prospect that the densest packings of tetrahedra might be truly disordered, or at least the fundamental cell is going to have a large complexity associated with it.
What are the upper ones?
I'm sorry?
Upper ones?
It's funny you should say that. I'm going to show you something. Okay, there have not been upper bounds, but I'm going to show you something in a second. Okay, now here's the other more amazing thing, I think. That if you put in the other Platonic solids that don't tile space, and you put in many particles in the fundamental cell, they all go to the densest lattice packings. In other words, one particle per fundamental cell. These are known structures that were obtained by various other people in the past. We didn't tell the computer to go to the lattice packing, and of course we didn't tell the computer to go to the densest lattice packing. It found it on its own. All right, so now this brings me to a Kepler-like conjecture for a class of polyhedra. So first of all, if you have polyhedra, if you want to make a high density packing, you like to have face-to-face contacts. Let me just show you. I forgot to show you my props. So these are tetrahedra, and of course, as soon as you say that in the case of tetrahedra you like to have face-to-face contacts, you immediately eliminate lattice packings because now they have different orientations. So that's a very simple explanation why tetrahedra do not pack like a lattice, the dense packings. Then it turns out that central symmetry of the object, so for the other three that I showed you in the previous one, enables maximal face-to-face contacts when the particles are aligned, it turns out. Now, as soon as you say that, then that's going to be consistent with a lattice packing when they all have to line up. And so this is just a two-dimensional picture of the situation, why that happens. Also, there's an upper bound, to answer your question, which turns out not to be a really good upper bound. There are no upper bounds in this business. This is a really poor one that sometimes is below 1 and sometimes is not. But it's the best we have. So if you have a better idea for an upper bound, I'd love to know it. But the point is, in some cases, when the asphericity of the polyhedron is small enough, the best lattice packing result is actually relatively close to this upper bound. So since it's a poor upper bound, that also lends some ammunition to the fact that, well, all of these considerations and other things that I don't have time to describe lead to the following conjecture, that the densest packings of the centrally symmetric Platonic and Archimedean solids are given by the corresponding optimal lattice packing. Here's another conjecture. The optimal packing of any convex congruent polyhedron without central symmetry generally is not a Bouvet lattice packing. By that I mean in the sense that the set of structures that are non-lattice overwhelms those that could be lattices, and there are going to be cases where they are lattices. Number 3, optimal packings of congruent centrally symmetric particles that do not possess 3 equivalent principal axes, for example, the ellipsoid, cannot be Bouvet lattices. Okay. So the conclusions, okay, sphere packings continue to provide challenges. Even in low dimensions, enumeration and understanding of all of the optimal packings, including the jamming threshold, we're really in the infancy, even there. The densest sphere packings may be disordered in sufficiently high dimensions, implications for the existence of short-range potentials with disordered ground states and perhaps coding theory. Non-spherical particles are not created equal, and there's so much that we don't know. And I want to thank my collaborators, Paul Chaikin, who is at NYU now, Bob Connolly, who is at Cornell, Alexander Donav, who was the graduate student that did the ellipsoid work and is now an assistant professor at Courant, Yang Zhao, who did the work on the superballs and the polyhedra, Antonello Scardicchio, who was a postdoc at Princeton and now is at ICTP in Trieste, And then Frank Stillinger, who I've done a lot of work with in packing problems over the years. Thanks for your attention.
Any questions?
Well, I have one.
Yeah.
Why cherry pick?
We have a model that has to do, you can think of it actually as a packing model, in which you allow a hard cherry pit, okay, to be impenetrable, and then you have a soft shell. And that was the model that we had to understand percolation. And my first postdoc when I came to Princeton was in charge of the machines, and he named it cherry pit.